And here we are in the topic, which is logistic regression. Maybe before we start to discuss about some specialties of logistic regression, and we will learn to compute some new stuff, I would like only to make some brief discussion about logistic regression in general. So previously in linear regression model, we try to apply regression into dependent variable that was cardinal or at least long ordinal scale. So it was one of the biggest assumptions for previous computations, that my cardinal variable should have enough values. Ideally, it should be dependent variable which is from -infinity up to +infinity. That's theoretical assumption. We know that, for example, prices were limited as the lowest price should be 0 or at least some positive value. So we were using, I would say, only half of possible values from theory, from -infinity to +infinity. But theoretical assumption for linear regression, or one of theoretical assumptions, is that cardinal variable should be as dependent with possible values from -infinity till +infinity. And now, and I would be happy if you can help me in this, I would say, preliminary debate. I'm asking whether, if I'm using social science surveys, mainly based on questionnaires, if I am usually using cardinal variables or variables with individual properties, so it means nominal or ordinal variables. So what is the most common variable which is flowing or which is the result from questionnaires? Ordinal? Cardinal? Do you think that most of questionnaires are getting cardinal data? Maybe that I wouldn't agree finally. So some other proposals than cardinal?
I think most of them are nominal.
Nominal, or maybe ordinal scale is also quite often applied, such as I totally agree, I totally disagree, or something like this. But once again, most of variables that are result of questionnaire surveys is nominal or ordinal variable. And the easiest variable, at least from statistical point of view, which is also result quite often from questionnaires, is only binary variable. So it means variable that can have only 2 possible values. So it means for simple case, I know that currently it will be big debate about this, but if I'm asking about sex of the respondent, usually I'm using only 2 categories, male and female. I'm not discussing about gender, as there would be currently big debate whether 100 genders exist or something more. So for simplicity, we will go into some biological insight and take only this binary variable. If I go back to our data file, we will be using for today mostly, so it means Titanic disaster. So I guess that you can help me to find what would be dependent variable for Titanic disaster, which is binary. So what would be our dependent variable? What's your guess?
Is it live or not?
Sorry, once again, louder.
Is it live or not?
Yeah, whether they survived or not the disaster, it would be dependent variable for us. So that's classical binary variable. Maybe before we start, we should discuss about possible dependent variables that are binary. So it means they have only 2 categories that can be applied in social science modeling. So do you have some proposals for other dependent variables that can be a result of our regression model. So it means proposals for application of binary logistic regression in social sciences. As mostly we are not trying to prepare a model whether somebody survived or not. That's usually not the problem of social sciences. That's usually a problem of some biological sciences. For social sciences, there can be some binary variable, I guess, as dependent variable. So some proposals for social scientists.
Age distribution.
It wouldn't be binary variable, age distribution.
Employed or unemployed?
Employed and unemployed. Yeah, okay. It could be whether I'm employed or unemployed, or if I'm unemployed, whether I will find a job in the next year or not. It could be, if you are students, what could be binary variable that can be present in some regression model.
Whether I am in the students club or I'm not.
Whether I'm a student or not, okay. I can also try to model whether you successfully pass a state leaving exam or not. So it means whether you successfully study or not. If you go into, I would say, ordinary life, so there can be discussion whether somebody will be married or not, whether somebody who is married will be divorced or not. So there are many problems that can be analyzed through this simplest case of logistic regression, which is based on binary. So the main goal of this, I would say, short introduction into the topic is that in social science, we have a lot of problems that can be computed by the simplest case of binary logistic regression. So it means in which we can apply dependent variable, which is binary variable. If I would get one more case, which is also very common. So for example, for political scientists, they will be preparing model whether somebody would vote or not, or would vote for some party or another party, etc. So these are another cases that can be computed by logistic regression. I will also add one more example, as we will be using such data later. So we will be discussing whether somebody is or was, as we will be using some historical data, internet user or not. So this is another case. So that's brief introduction into logistic regression. And the first step we will be discussing will be, I would say, maybe a little bit theoretical, but I guess that it is also very practical insight into logistic regression, and also for computations, we would need to know about these concepts. So that's why we will be, I hope so, making brief recap of discussion about probabilities, and then we will enter a new topic, at least I guess for most of you, which is discussion about odds and odds ratios, or in a more general language, I would discuss instead of odds about chances. So also in Czech language, we use the expression chance for the odd, so that's why we can also use English general language term, which is odd. So here it is, and here we are, and let's discuss theoretically and also practically about probabilities and odds. For practical insight, and it will be for us maybe more important, I will open some file which is prepared on my computer. So here it is, and here I have slightly simplified results from Titanic data. So here we have rows that are created by male and female, and columns, whether they survived or not. Survived means yes, and didn't survive, it is labeled as no. So here we have sample size, which is approximately 1,200 currently. And our data file, which will be present in Chemovi in the next few minutes, will be nearly the same, only I slightly rounded up or down these figures for simplification. So here we have male and female data about survival or about dead people in Titanic. And first of all, here we know that 600 male didn't survive, 150 survived. For female, the proportion is slightly opposite, 150 died and 300 survived. So first of all, I can compute the probability of survival or not survival. So instead of these observed counts, I can compute probabilities. So I would type that I would be computing probabilities. I would once again copy no and yes. I will once again copy male and female. And my first question is, what is the probability that male didn't survive? So what should be the value here, or what should be the formula or equation written here? So first of all, it would be maybe good to sum up all male and all female passengers. So I would make sum for simplicity here. So 750 and 450. So here it is. And I guess that probability of male to be dead by this Titanic disaster can be computed as 600 divided by 750. So according to my opinion, the probability of male to not survive Titanic disaster would be quite high. So if I computing, maybe I can add some more decimals here. So it is 0.8 approximately. And if I would like to compute the same probability for female, and if I don't like to repeat the computation, I can simply fix this column. So I will only change the style of this equation. So I would need to go into column D. So here it is, 0.8, and this must be 0.2, as both these probabilities must sum up into 1. As you must die or survive on Titanic disaster. There is no third option. Once again, that's binary dependent variable for us. And if I would like to compute the results for female, you can very simply see that for dead females, the probability would be quite low, I guess 1/3, and 2/3 to survive. So if I compute these probabilities, I can compute it by this previous formulas present in my Microsoft Excel, and I can see 1/3 for not survival and 2/3 for survival. So these are probabilities. So instead of these observed counts, I can here compute probabilities. If you don't like probabilities, and mostly in contingency table, this is not something more than classical contingency table, 2 times 2 table, the simplest case. You can also ask for percentages. So if I would apply percentages here, I would get row percentages here as another insight into data. And maybe this is maybe more common for you. Once again, I will go into probabilities, as we are mostly discussing about probabilities. And we know that probability of individual event, so it means whether you didn't survive or yes, is observed count for this option divided for all options I have. So that's the probability. And still, instead of 4 figures here, I have 4 probabilities here. And still the problem is maybe a little bit complicated to describe. I would need to read out all these 4 figures, and then maybe I can answer the question. is there some relationship between survival and gender or not? Can you help me to answer for this question according to these values? Was probability of survival somehow related to gender or not at Titanic? Or are these phenomena independent?
My guess is that it was.
Yeah, it was, as 80% of male died, but for female, only approximately 33. So it is somehow related. I would say maybe strongly related. So if we would decide, for example, to compute classical contingency table analysis, so it means to compute chi-square test, contingency coefficient, etc., and we would discover some relationship. Okay, so that's about probabilities. Second step, and we know to discuss about this step, as we would need to understand to this concept for later discussion of results of logistic regression, is discussion about odd, or in plural, odds. Once again, you can use instead of it general expression chance, but be careful if you are discussing about statistical results. We mostly in English use the expression odd. What is the odd? Odd is nothing more than ratio of probability of the occurrence of the event and probability of the non-occurrence of the event. So in other words, I would be computing some ratio of these two probabilities or of these two probabilities. So I can compute odd for male and I can compute odd for female. For simplicity, as the first column is no, I will be computing odds or chances whether they didn't survive or chances to die. In other words, I know this is not a very nice expression, but currently we are totally out of some values. We are in statistical computations, so sorry for that. I would be computing odd, so that's why I'm typing odd here. And once again, it is the ratio 0.8 divided by 0.2, and for female 0.33 divided by 0.67. These figures are very nice to us, so I guess that for the first insight, we can compute results, so it means odds, directly without Microsoft Excel. So 0.8 divided 0.2 is approximately, is 4, or in other words, and once again, it is the ratio, so that's why I will type it is 4 divided to 1. For you to remember, sorry for that, I will need only to change formatting. So currently it should work. So it is 4 divided by 1. So it means that from 5 male on Titanic, 1 survived and 4 were dead. So that's this ratio, 4 divided to 1. Or if you like to compute it, it would be only 4. So if I will ask SPSS or Microsoft Excel for computation, it will be 4 only. But if you see the value 4, you maybe do not remember that this is the ratio of two probabilities. So once again, odd is ratio, that's why I'm typing here 4 divided to 1. The same ratio can be computed for female. Once again, the first computation will be only by my head. So if it is 0.33, 0.67, once again, 1/3 and 2/3. So it is 1 divided by 2. Oh, sorry for that. Currently it is correct. So once again, if you have 3 female passengers on Titanic, 1 on average died and 2 survived. So this is the ratio 1 divided by 2, or if you like, 1/2 would be here, I guess, if I would make computation. So 4 and 0.5 are different odds. And if these odds are different for male and female, it means, in other words, there is some relationship between survival, not survival, and gender. So we can also describe relationship instead of these 4 figures or 4 probabilities by these 2 odds. Before next step, sorry that maybe you are too slow for this first insight, but it's crucial for you to understand 2 odds. And in next step, we will discuss about odds ratio. But before we start to go further, I would like to ask you if you can try to find theoretical minimum and theoretical maximum value for odds. So what could be the lowest value of odd, if you know this is ratio of 2 probabilities, and what could be theoretical maximum of odd? So proposals?
There are none. It is impossible to find.
I would say like close to 0 and to infinity.
0 up to plus infinity, yeah? As if this value will be nearly 1, and this will be close to 0, it will be plus infinity, and just reverse case would be 0, yeah? Of course, that we know that if this would be 1 and this would be 0, it is not defined, but for practical reasons, so it means for modeling of real-life issues, we know that maximum distribution of these no's and yes probabilities, or 0 and 1, if we choose a general description of binary variable, should be at least 0.05 versus 0.95. So if it is more extreme, there is no space for computation for explaining the variance. So that means that in real life, we will not find odd that cannot be computed in real life data. So that's the first insight. So, okay, from 0 up to plus infinity. And now, I know maybe it is a little bit complicated, but please try to imagine axis from 0 up to plus infinity. If you didn't meet plus infinity previously, maybe this is the first time during this lecture. And now take into account that this very, very long scale, or very, very long axis from 0 up to plus infinity will have, for analytical reasons for us, the middle into the value 1. As if the value of odd would be 1, it would mean that probability of no, yes, or 0, 1 would be the same. So for example, if there would be some category in Titanic for which the amount of survivors and those who died is the same, it would have odd 1. 1 divided by 1 would be formally description of such odd as ratio. So once again, the long scale from 0 up to plus infinity in odds is, in other words, asymmetrical, as 1 is the middle, and there is only from 0 to 1, 1/2, and 1/2, which is much bigger, according to our opinion, is from 1 to plus infinity. So that's the first insight. We can see that for male, this is much bigger than 1. So it means that more male were dead during Titanic disaster than survived. Just opposite result, so it means all below 1 means there are more people in the second category. So it means more female survived than died on Titanic disaster. So that's the first meaning of the value of odd. So above 1 or below 1. Above 1 means more in the first category, below 1 means more in the second category. So I guess this is very, very clear and easy to understand. And one computational trick, or trick for interpretation of results, I would recommend you, and this is not only my recommendation, but generally in statistical textbooks related to these models, if your odd is below 1, so it means instead of saying that the odd of odds to be dead for female was 0.5, so try to reverse this value, or we call it inversion in mathematics. So instead of 0.5, I would take 1 divided 0.5, which is 2 divided by 1. And if I am reversing or inversing mathematically these values, I would need also to reverse the interpretation. So it wouldn't be odd to be dead, but it would be odd to survive. So if I am reversing the ratio, I need also to reverse the interpretation. So that's a computation trick. So if you will find odd or odds ratio, which is below 1, every time try to reverse the value and the interpretation. It will be much easier for you. As it could be descriptions such as that female had something like 0.5 chance to be dead, and that's quite strange to interpret. So 2 times higher chance to survive is much better for the interpretation. So that's for odds. We know about the scale from 0 up to plus infinity and middle point 1. And now I will go back to the presentation. We know about odds. Only in the literature you can find simply the O letter, which is standing for odd. So if I would be using some theoretical insight, so I would be describing this odd for male, something like O with small index m, for female O with small index f. So it would be possible. And I would skip into the last, or at least last for this moment, description, and we will try to make ratio from odds. Previously, we made ratio for probabilities, and the next step would be to compute ratios from odds. So it means that we will make ratios from original ratios. So it is maybe slightly complicated stuff, but still, this ratio of 2 odds is called odds ratio. In the literature, you can simplify it only OR description. So that's odds ratio. If I will go back once again into Czech language, odds ratio in Czech language, je poměr šancí. So here we are once again, and currently I will be computing odds ratio for odd to be dead for male and to be dead for female. So I will take 4 divided by 0.5, or in other words, I would be taking fractions 4 divided by 1 divided by the second fraction 1 divided by 2. If you remember the rules for division of fractions from mathematics, so final result would be 8 divided by 1. If you do not believe, you can compute it for a simple case. So I would be computing here. So it is 8 mathematically. And if I would type it correctly in mathematics, so I would need some space. I would be computing 4 divided by 1 divided by 2 by 1 divided by 2. And rules for computation, such a complicated fraction is to take nominator for the first fraction and denominator for the second one. These must be multiplied, and also the rest must be multiplied. So 8 divided by 1. So I will type it here. So it is 8 divided by 1. So here it is. So once again, I'm typing here this ratio for you to remember this is the ratio. And what does it mean if odds ratio here currently for not survival, survival, to be dead or not to be dead, for male and female is 8:1. So does it mean that there were more male or female dead, or there were more male than female survived?
Well, it means neither of them. It means that on the long run, or in the bigger scale, or no, that means if the numbers of female and male were the same, you could say that more male will probably die.
Okay. So I would rephrase the question. Does it mean that there was bigger probability to die for male or female? We can take it. Yeah. Sorry. So of course, but still, number of passengers wasn't totally equal, but it was quite close to equal. So we can also take it in absolute values. But you are definitely right. Okay, so it means that probability of male to die was maybe bigger than for female, but be careful. It doesn't mean that probability for male to die was 8 times bigger than for female. Let's try to compare probabilities. 0.8 and 0.33. It's not 8 times bigger. If I compute this ratio of these probabilities, and there is no formal definition for this ratio, so but I will compute it for you. It is 2.4. So ratio of probability is 2.4, but currently we are computing odds ratio, which is not ratio of probabilities, but ratio of odds. So that's why odds ratio 8 doesn't mean that the probability is 8 times bigger or lower. It means there is some unequal probability for these two groups, but it is not evaluating the level of this inequality for probabilities. Once again, it's odds ratio. Okay, last comments or last discussion that should be related to this step should be once again about theoretical minimum and maximum for odds ratio. So what could be the minimum value and what could be the maximum value for odds ratio? For probabilities, we were making fractions for two non-negative values between 0 and 1. Currently, we are taking fractions from values that are from 0 up to plus infinity. So what could be minimum and maximum? 0, maximum. Once again, plus infinity. So this is the same. For odds and odds ratio, there is the same theoretical and minimum and maximum. Okay, great. And once again, I would like to repeat the previous rule. So this quite long scale from 0 up to plus infinity can be divided into 2 halves, and the middle is 0.1. And 1 here for odds ratio would mean that probabilities to die or to survive for male or female were equal. So it means there is no relationship between gender and whether I'm dying or not. It would be odds ratio of 1. So in other words, if I go into the logic of contingency table analysis, it would mean there is no relationship between variables if odds ratio is 1. So another option, but we didn't discuss this topic during statistical lectures, for evaluating of relationship in contingency table, which is 2 times 2 only, is not to apply chi-square test, but only apply odds ratio and evaluate odds ratio. There is also formal test for odds ratio, which is the same as chi-square test. So that's another option how we can enter into this topic.
For example, we had an apocalypse, and there would be it would be equal probability for women and men to die because there would be different factors such as distance to bunkers or something like this. So that would mean that the odd would be 1 because it doesn't depend on whether you're male or female.
Yeah, definitely it would be the case, for example. Okay, here it was very easy on Titanic disaster. If you remember, I don't know if you read some book or watched some movie or document, especially female and especially kids were the first one to leave the Titanic, and then they found there is not enough space for the rest people. And also, we will see there were some differences for people from different classes from Titanic, but that's our next step. So this is further description, and if I would try to sum up also this description. So originally, there were 4 figures describing contingency table by counts or by probabilities. Instead of these, we used for description or for easier description only 2 odds. And finally, we used only one value, which is odds ratio. So this odds ratio, 8 or 8 divided by 1, can be seen also as descriptive statistic for my data, which is describing these 4 original cells. So you can also see odds ratio as descriptive statistic for my data, describing the patterns of relationship in my contingency table. So that's also the goal of this odds ratio. And once again, we know, or at least you should have some idea, that this odds ratio could be somehow tested. So it means I can evaluate whether my relationship could be also present in some more general data. I would like only to give one small warning here. We are describing, and we will be also computing data from Titanic disaster. And Titanic disaster, according to my opinion, and maybe I'm the only one in this classroom, is not any random sample. It is the whole case, I would say, whole population of those people who are present on Titanic. And this is not some random sample from all disasters on the sea or something like this. So that's why we will be mostly in Titanic data describing the situation on Titanic, and we will not try to infer results from general population. So we will not be mostly performing some statistical tests, etc., etc. So it will be our first topic. So we will discover that for logistic regression, and the same could be also applied for linear regression, sometimes could be descriptive technique for my data. So maybe I do not need any testing, etc., etc. Then we will go into some sample data about internet usage, and we will be also using tools such as some statistical tests, etc. So this is only first warning here. So here we have 8:1, and once again, 8:1 odds ratio is description that ought to be dead, and ought to be dead means probability to be dead versus to be live. So once again, that's ratio. So ought to be dead is 8 times higher for male than for female. That's first possible interpretation. And once again, I can also reverse the interpretation. Ought to survive. So once again, to survive versus to be dead, that's the ought. For female, so if I reverse categories currently, so ought to be live for female is 8 times higher than for male. So this is also another option for interpretation, that you can reverse both categories in my contingency table. And once again, for us, for logistic regression, one variable would be dependent, currently here whether I survived or not, and one would be independent, so it means whether I'm male or female. So this is how it works, and that's description about odds ratio. And last one comment, and maybe the most complicated, so sorry for that, that we will finish this first part of the lecture by the slightly complicated step. So we know about odds ratio from 0 up to plus infinity, and we discussed also that for linear regression model, it would be nice if our values would be from minus infinity till plus infinity. And my question would be, but I will not discuss for a long time, whether you know some mathematical function that will change original values from 0 up to plus infinity to the values that could be all real numbers from minus infinity till plus infinity. Do you remember some function from mathematics that can do this stuff? Power will still, from positive values, will be positive.
No, I'm sorry, it's the square root or something.
Square root will be still positive from positive values.
So, because if you make a square root, the outcome is always plus and minus. You know, it's positive and negative. Because the negative
yeah, but that's special definition, I would say. So I would go into description of so-called logic. So the last step And I must warn you that in logistic regression, and you can hear similarity logistic regression Logit, there would be some more transformation. We started compute odds from probabilities, odds ratio from odds, and last one step would be to compute Logit. And Logit means that I would be computing logarithm from odds or odds ratios, from original values in the range 0 up to plus infinity. If I compute logarithm, and if you do not remember, let's go back into your secondary study for mathematics. If it is nightmare, please don't go back. But if you take logarithm, and once again, we don't need to compute logarithms. It will do us for us Jamovi, JASP, or SPSS, or another package. But computation of logarithm will give the value from minus infinity till plus infinity, and will also give you symmetrical scale. So only very short recap of the properties of logarithm function. So if there is a point 1, once again, this is the middle for odds or odds ratio, from logarithm of 1 would be 0. And 0 is classical middle of minus and plus infinity, and logarithmic scale for odds or odds ratio would be, that's why, symmetrical. So from 0 original, it would create minus infinity. For plus infinity, it would create plus infinity. And for point 1, which was once again in artificial middle for odds ratio, it would create 0. So logarithmic scale at least is symmetrical around 0. And if there was odds ratio, which was balanced probabilities for both groups, 1, Logit for this odds ratio would be 0. So no effect, no relationship in Logits would be 0. And positive and negative values would be the same as the values above 1 or below 1 for odds ratios. So that's Logit. And we will get these Logits as the basic. So for logistic regression, there are 3 transformations. First of all, I would be computing probabilities, from probabilities odds ratios, and logarithms. And these logarithms for odds ratios of dependent variable then will be modeled by classical linear regression. So it means by individual predictors. So dependent variable in logistic regression is Logit, and independents are classically described as intercept plus the impact of the first predictor plus the impact of the second predictor, etc., etc. So there's a trick behind logistic regression. And currently, you should be able to understand to this logic which is behind. Only be careful, and that's why it is in red color currently here in front of us, that probability is not the odd, and odd is not Logit. So these values are totally incomparable. But of course, once again, if Logit would be positive, in our case, for example, in Titanic, it would mean that odds ratio is above 1, and it would mean that probability of the first category currently to be dead for male is bigger than for female. So from positive value of Logit, we would recognize that there is some relationship, and currently relationship would mean here that more male than female in relative interpretation died on Titanic disaster. So that's the first insight into the topic of logistic regression. And before we will enter into some more stuff about binary logistic regression, we would make a break. We would be briefly discussing, and then we would be computing this tightening data, it means, in Jamovi. So we will try to force Jamovi to compute these values, especially this value approximately 8. There would be maybe slightly different value on tightening data, as once again I slightly round up and round down these values, but we will find some similar results on tightening data. So some questions so far? Okay, so if there are no questions, So here we are in the description of binary logistic regression. I guess we covered nearly all necessary steps. So I would briefly only go into the literature. So if you like to know more about logistic regression, there are some, I would say, very detailed books. One of classics written by Hosmer Lemeshow is called Applied Logistic Regression, especially those who are interested in biology and medicine would like this book, as this is classical literature for these people. According to my opinion, maybe the best book in the field is called Regression Models for Categorical and Limited Dependent Data, written by Scott Long. There is also the version which was written by Scott Long for Stata software package. And if you like to have some brief insight, there is also a very nice small book written by Fred Pempel called Logistic Regression in Primer. If you like to be specialist in the analysis, not only in logistic regression, but in all related procedures. So it means procedures for so-called categorical data. Categorical data means nominal and ordinal variables. You can read the book written by Agreste. This is something like Bible of categorical data analysis, and Agreste is the biggest classic in this field. If you like to apply logistic regression in SPSS, so you can read a field textbook, and also very nice chapters about logistic regression can be found in Nourish's Statistical Procedures Companion and SPSS book. And for those who are Czech readers, the best title is article written by Blanka Řeháková, which is called simply and nicely, Don't be afraid of logistic regression in English, česky nebojte se logistické regrese. And you can also find 2 chapters about logistic regression in textbooks, which was written by me and colleagues from Masaryk University, Professor Mareš and Rabušic. If you still do not have this book in your libraries, so you can buy it in Jana Bojanova office. So that's my recommendation. And I would like also to announce there is a new book on the market about some advanced procedures which are closely related to this course, which is also available according to my knowledge in Jana Bojanova office, which was currently issued by Masaryk University, and I'm the only author of this book. So here it is. Let's go through some basic division of logistic regression models. Currently, and for the rest of today's class, we will discuss about the simplest and most common logistic regression model, which is called binary logistic regression. And this is the model for binary dependent variable. Once again, we discuss about survive, not survive. We will discuss about internet users, non-users, but we know about much broader capabilities of this procedure. There are also 2 competing models for logistic regression that can be applied. Ordinal for ordinal dependent variables. We will not discuss about this model in detail. I will also make some small comments. And there is also a special model for nominal variables that have more than 2 options. It is sometimes called polytomos, sometimes multinomial logistic regression. And we will try also to cover this analysis by library data, which is data file which is available for you once again in SIS. I would like to say that in Gemovi, and that's quite nice, all these options, so it means binary, ordinal, and multinomial or polytomos logistic regression analysis is applied. The same situation is present in SPSS package. Unfortunately, in JESP, still there is only binary logistic regression applied. So that's the difference. If we would like to know about some very close technique to logistic regression, so the closest technique, so it means dependent is binary or nominal variable, is discriminant analysis. So that's the first insight. And as far as we know from previous description, we take logits for a dependent variable. So we take technically a so-called natural logarithm, which is logarithm with base, which is Euler's number. It is approximately 2.71. And this logit is the dependent variable for us, and independence then follow the logic of linear regression. Maybe it would be good to type some equation for this example. So I will take, for example, the case of survival on Titanic. So I would be computing logarithm, that's why I'm typing ln, which is usually shortage for natural logarithm, and I'm taking logarithm for probability, and for simplicity we will do the same. So non-survive would be the first one, probability divided by probability to survive. Mathematically, we could also type that it is probability of 1 minus probability of non-survive. That's would be the same. So probability of survive versus non-survive. So that's a dependent variable or left-hand side of the equation of logistic regression. So you can see here the transformation which is present in logistic regression, and then we perform the model. So we would take some average, but be careful. Average means here average logit level of this phenomenon. So there would be some intercept. And then we will add the impact of the first predictor. So I would type for simplicity big B instead of beta, as I would need to find some special symbols. And for example, the first predictor could be, as we discussed previously, gender. Second predictor could be, for example, whether you are old or young. So it could be, for example, age. I will only change, it would be B1 or beta1, beta2, etc., etc. So we can add more predictors. So this is the formal equation for logistic regression. And the problem, or at least a problem for possible interpretation, would be that these estimations of these betas, so it means usually small b's are coefficients or slopes, would be in logit units. And now the question is, who can interpret the values of impact of individual predictors in logit scale? Most people, and please believe me, I have quite a big survey behind, as I'm teaching logistic regression approximately 15 years. So most people are not capable to think in logits. So logit scale is not natural scale for the interpretation. So that's why maybe it would be good to somehow erase logarithm here, and at least to discuss in odds ratios, which would be the scale if I would omit these logarithms. And now, once again, the question is, once again, maybe for some of you nightmare from secondary or upper secondary education, what is inverse mathematical function to logarithm? Does anybody know what I need to do to erase, or that's not a mathematical expression, but to cancel logarithm here? So I would take this equation and I will try to give you a hint. So if I would like to change logarithm into non-logarithm, so it means from logit to odds ratios, I would need to exponentiate. So exponential function is the inverse function to logarithm. So if I exponentiate logarithm, there would be nothing, or number 1 could be present here. So I would need to exponentiate. That's why I would type exp, and in brackets would be the whole right side of this equation. I've only changed it slightly to have only one row here. So I would add 3 points here, as it could be also longer expression. So if I would exponentiate, an exponentiation could be made by calculator, by Microsoft Excel, or by statistical packages. Fortunately, I would get results in the scale, which is maybe much better for interpretation, which is odds ratio. And maybe you would like to take one more step to go back to probabilities, not only to odds ratios. So there would be some more computation that I would express probability of non-survive as some expression. We will try to make this procedure next time, as I will show you also some trick how we can graphically interpret results from logistic regression, but it would be next time. So that's the first step for us. And once again, we know that we would be exponentiating all these individual coefficients, or once again, packages such as Gemovi, Chess, or SPSS will do it for us. I hope so. So that's promising, and we will discuss later about next steps, but I would propose currently to open Gemovi. And in Gemovi, we will open Titanic CSV data file. So I will try to find it. You can click into open and find the file, as I have it opened from yesterday, so I can take only Titanic. Oh, it cannot be found, so I will try to find it once again. So I would need to find a way, so not in downloads, but disk T. The course of advanced data analysis. And oh, sorry, I opened another file. So once again, should be careful. So Titanic is already opening. So I will only close the second file to have only one file currently open. And here we have data file from Titanic disaster, which is very, very famous and quite good to enter into the topic of logistic regression analysis. So the first column is for us not very useful. These are names of individual Titanic passengers, so we will not go into this column at all. You can see that's real text data. So once again, we don't need it. Then there is a second column, which is class on Titanic. I guess there are 3 classes present here. And as far as we discussed previously, we expect that probabilities, odds, or logits were not the same for individual classes. It is expected, I guess, that those who are passengers of the first class have a bigger probability to survive in comparison with the rest, and also maybe the second class is slightly better than the third class, as the evacuation on Titanic was ranked according to these classes. So as the first variable, so that's classical nominal variable, at least here in this data set. Then you have cardinal variable, which is the age. Do you expect there were some relationship between age and survival on Titanic or not?
Those older ones will have higher survival rate.
Older?
I would probably expect it to be the other way, like children and women.
Yeah, kids maybe. Okay, so at least we have 2 opposing hypotheses here. Let's see in the next analysis. Then here we have the basic predictor for us, male versus female. So we know there will be some disparities, and our dependent variable would be survived. 1 means yes, and 0 means no. So that's all for this options. Only I would like to show, and then we will make this trick active through logistic regression, that if I click into some of GMOV variables, the same style is applied in CHESP, I can change the ordering of options. So instead of first category 0, I can make the first category 1, and it would have consequences whether we will prepare model for survival or non-survival in logistic regression, for example, here. So it would change our results. Currently, we will not change this, but I will show you that it works in GMOV and once again in CHESP environment as well. So before we will enter into logistic regression in GMOV, but I can give you a hint that we will find regression. And here we have 3 models for 2 possible outcomes, binomial or binary logistic regression, for more options in nominal variable multinomial, and there is also ordinal version of logistic regression here. But before we start, it will be good maybe to compute a real contingency table for Titanic data and to see differences from our previous computations. So if you like to compute contingency table in GMOV, you would go into frequencies. And here there is signed contingency table, and here we have independent samples, chi-square test of association, etc. So that's the procedure for classical contingency table analysis in GMOV. So if I click here, I should compute a contingency table, I guess. So I will combine in rows sex, and in columns, I would combine whether they survived or not. So here we have, I would say, real contingency table from Titanic data. And I can take this table and copy into Microsoft Excel environment to our previously slightly artificial data. So here we have real life table. I guess the dimension here is nearly the same, only female are above male. So that's the difference. But I guess that's not a problem. So I can briefly try to recompute results from previous computations. So first of all, probabilities. So here we have probability for female to be dead. And the same, I will only erase this column for simplicity, and I will only fix columns for computation. So here we are 1/3 and 2/3 for female, and approximately 83 and 0.17 for female. So these figures are quite close to our previously computed results. Only previously computed results will be maybe slightly more smooth for next computations. And if you would like to compute odds, so once again, it's very easy to perform such procedure. So here we have the first odd 0.5, the same as previous one. And for male, it is approximately nearly 5 in this case, not 4. And if I compute odds ratio, what would be odds ratio from 5 and 0.5? From 4 0.45, it was 8, or I divided by 1. Currently, it would be 10 divided by 1, approximately, or 10. Yeah. So I would compute it for simple inside. So here we are. And here we have odds ratio, which is 9.98. So please remember this figure, as you will try to find this figure also through results in logistic regression dialog. So this is the first inside. I will only go into some details. So if you would go here into statistics, and the same style can be found in CHESP as well as in SPSS, you can directly ask for odds ratio. So here it is. And you can also ask for logarithm of this odds ratio. So here it is. Only be careful that odds ratio currently is 0.1, as it is computed 0.5 divided by 5. So this is only a reverse ratio, but still the same value. And here we have the Logit, which is logarithm from 0.1. As it is below 1, it must be negative, and it is minus 2.3. So this minus 2.3 will be coefficient or slope in our logistic regression, as once again, original scale for computational logistic regression will be in Logit. So this minus 2.3 will be our result. So that's it for the first insight. And now I guess we can enter directly into the dialogue for logistic regression. So regression and two outcomes, binomial would be the first one option here. And you can see that by default, I guess this is quite similar to linear regression outputs. We are expecting two tables, some with model fit and some with model coefficients. So I guess this is for us enough. And dependent variable, once again, for us is whether they survived or not. And independent variables, once again, are differentiated into two parts here. Covariates, it means variables that are independent and are cardinal, as you can see measurement picture here, and factors that are expected to be defined as nominal. So I guess that we can move sex here. And I expect that in few seconds there will be computation. And for the first insight, I would ignore the first output. So it means description of model fit. And I would go only into this model coefficients. So there is some intercept. I would say this is some general level, but once again, be careful of Logit survived versus not survived. So that's quite complicated to explain or at least interpret easily. But here we have sex, male, female, comparison, minus 2.3. And I guess that we know this value minus 2.3 from previous computations. Once again, here it is, and it was logarithm of odds ratio minus 2.3, which means that odds ratio is 0.1. And once again, only be careful that currently our values are reversed in previous comparison. So we are comparing male and female, but not non-survival, but survival. So non-survival odd for male is 0.1 of the same for female. And maybe this is slightly complicated. That's why it would be good to inverse the value or reverse the interpretation. So once again, for values that are below 1, that our odds ratio, is much better to change the interpretation and inverse the value. But still, as the first step, I would ask for some more values. And here, if you will visit the first, second, the fifth option, which is called model coefficients. So it will offer for you odds ratio instead of original Logit. So instead of minus 2.3, I would get 0.1, which is at least very simple to inverse. So 0.1, if it is in ratio 1 divided 0.1, it would be 10. So I would ask for odds ratio. And I guess that here we have the last column, which is 0.1 odds ratio. So it means exponentiated value from minus 2.3 is 0.1. If you do not believe, we can ask Microsoft Excel environment. So I would compute exponentiated value, exp minus 2.3 and it is 0.1 blah 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 some more digits as it is not maybe directly minus 2.3 but minus 2.301 and maybe some more digits later. So here it is. So it means automated exponentiation and odds ratio. And once again, for odds and odds ratios, we usually prefer not to interpret values below 1 but above 1. So you can do it alone, so you can reverse or inverse this value and reverse the interpretation, or you can also go back into data matrix, and you can, for simplicity, change coding of this survive variable. So if I double click into the variable and I would move the first option up, I guess that Jamovi will recompute for us results automatically. Oh, it's not working, so I guess it's only in JESP present. So I would need once again, I guess, to compute logistic regression. Sorry for that. So once again, I will add survived as dependent, sex as independent factor, and once again ask for odds ratio. And currently it works. So sorry for that. There is small difference in JESP and Jamovi. In Jamovi, if you change these codings, filtering, etc., it will influence only later outputs. In JESP, it will influence all outputs. So here we are. Instead of minus 2.3 coefficient, we have the same value with positive sign, 2.3, once again in Logit. But the most important for us is the value 10. And now it would be good if somebody would try to interpret this value of 10. So if you try, doesn't matter whether you are here in the classroom or connected via Zoom, but please try to interpret this value of 10, as it would be good to understand to this first value, which is the most important result for this first insight in logistic regression.
Odds to survive is 10 times higher for women than for men.
Okay, takže odds to survive, which means probability to survive versus not survive for female is 10 times higher than for men. Yeah, that's great. Okay. Once again, be careful. It doesn't mean that probability to survive for female is 10 times higher. The ratio for these probabilities will not be so high. We can compute it very easily. If you go to Microsoft Excel environment once again, and if I make the fraction 0.66 divided by 0.16, so here we are. Once again, so it is approximately 4. So odds ratio 10 means here, in this case, ratio for probability is approximately 4. So be careful and do not mix the expression of probabilities and odds. So they are not the same, once again. But still, it means that the chance and as well as probability for female were much better than for men. Okay, so that is the first insight into logistic regression, and I guess that in combination with previously discussed contingency tables and computed results, we fully understand what is this value 10 about. So this is only descriptive statistics for contingency table, I would say, for this first insight. And you can see that there are some more figures here included. So there is some standard error called as SE. There is also some Z statistics. So it means this is some test criteria computed very simply as the estimate divided by its standard error. So this is the same style as t-test in linear regression. And here we have the evaluation of the test. But once again, we would skip these results for this Titanic example, as we do not try to infer results to any bigger population of all catastrophes on the sea or something like this. So we use currently binomial logistic regression as descriptive tool only. And that's why maybe we'll also omit other characteristics such as model fit measures. We will discuss about these in the example which will be devoted to other case, which is usage and non-usage of the internet. So that's it. And this is our, I would say, first binomial logistic regression model. And next step, of course, would be quite straightforward. If I go back into my data matrix, I can add some more predictors. So I can once again answer the question whether there were the same probabilities or odds for people from different classes. And we have two competing hypotheses here about the impact of age, whether older or younger people were more preferred during the evacuation. We would add some more predictors, at least class and age. One is cardinal and one is nominal, as you can see. There is no more space here, as to include name would be total rubbish, and I guess the GMOV also wouldn't allow to include the name into the data, so that's impossible. So first of all, we would add these two variables. For age, it would be quite simple. That's cardinal variable, so it means one coefficient will be computed. But for class, it will be slightly maybe more complicated, as there are three classes here. So it means it's nominal variable with three options. And we know from linear regression, and logistic regression is nothing more, as you know from previous discussion, only left-hand side is transform dependent variable into Logit scale. So we know that original nominal variable with more than two options cannot be included directly into linear regression model, but instead of original variables, we need to create what? Yes, set of dummy variables. And we know, fortunately, that dummy variables, also in linear regression dialog in GMOV, can be created automatically for us, and the same style is applied in logistic regression. Fortunately, also in SPSS environment, in logistic regression, these dummies are created automatically for you. Don't ask me why. In linear regression, there is no such option, and in logistic regression, there is option. But in logistic regression, whether you apply computation in GMOV, JASP, or SPSS, all these packages can create for you dummies automatically. So there is no necessity to add anything more. So I would go once again into analysis, regression, and binomial or binary logistic regression. And once again, I would take survived as dependent variable. I would take sex as independent variable, and I would take as the first step age as we would need to say which of two competing hypotheses is correct here in the classroom. So let's cover it. And here we have some computation. I would also add for model coefficients odds ratio for this first inside. So it means instead of original estimates that are in Logit units, we would get odds ratio scale. And currently, we would need to find what is present here. So once again, here it is written that we are comparing male and female. And we know that for male, survival or non-survival was bigger chance.
For man to die.
For man to die, yeah. So we know that that odds ratio, if it is written that it is male comparison with female, means that it is a comparison of those who died versus those who didn't die. I would like to say the logic, which is usually behind the scene in software packages in logistic regression, is that you take the second category as the more important to the first one. And as we reversed categories once again in survived, that 0 is the second one. So we are currently modeling you died or you didn't survive. Yeah. So if I would reverse it, I would be modeling survival. Yeah. So that's only necessary to know for other interpretations. So I would go back to these results. So
numbers change, like estimated and odds were before 2.3 and now it's 2.47.
Yeah. I would explain it. So, but be patient, at least some minutes. Thanks a lot. So, first of all, currently, once again, we know that male-female difference is approximately currently 12 evaluated by odds ratio. And once again, it is odds ratio to be dead. Bigger 12 times for male than for female. And now I will like to answer the question why currently it is 12 and previously it was 10. This is a classical phenomenon that if you enter new variable into the equation, doesn't matter whether it is logistic regression, linear regression, or any statistical model, your coefficient, doesn't matter whether it is estimate or odds ratio, these are only recomputed from each other, can be changed. And the reason behind this, that maybe two of predictors or more predictors are somehow related. And currently, we are computing, I would call it as pure impact of gender. We control the impact of age. Previously, and you can check it by some descriptive statistics. So previously, it is expected, according to my opinion, that age structure of male and female wasn't totally equal. So it means that, for example, average age for male and female wouldn't be the same, age structure wouldn't be the same, etc., etc. So original value of 10 or approximately 10 of this odds ratio, male versus female, non-survival, was slightly biased downwards. Maybe the reason was some unequal age structure for male and female. But currently, we are, I would call it, equalizing the age structure. Equalizing means in statistical modeling that we will enter or control the variable into the model. And if we enter the variable into the model, we control values of this variable, and we check for the impact of this variable, and we would get pure effect. So currently we know that the difference or ratio for male and female is even bigger. So currently, I would say age is under control. That's why usually also these coefficients, if we add some more predictors, are sometimes called as partial. Original, it was only the impact of one variable, so it would be called bivariate coefficient. This is the same style as for correlation. And currently I'm controlling some more variable, and that's why this coefficient would be called as partial. So it means this is the difference or ratio male and female if the age is under control. Maybe that also other variables are important to control. So maybe also we would add, for example, class for passengers, and also this value will be changed. So this will be our next step. So if you have some doubts that other variables can somehow influence your results, enter these variables into the model. That's my conclusion. Okay, so I hope that this answer is enough, and we would now a little bit, we will have a little small fight with the interpretation of the age variable. So first of all, we can see positive estimate in Logit, as well as odds ratio slightly above 1, but slightly, very slightly above 1. This is nearly 1 and this is nearly 0. So first of all, what I would like to say from substantive point of view is that the impact of age is quite small one, it seems to me, but be careful we are currently interpreting the age change by 1 unit. So currently, we are using the same interpretation as for linear regression. If my independent variable will increase by 1 unit, what will be increased? Currently not in dependent variable, but in Logit for dependent variable. That's dependent variable in logistic regression. But still, it seems that the impact is very small one. Doesn't matter if we are looking for estimated Logits or odds ratios. But if I would like to solve the puzzle whether older or younger were more prone to die or survive, as we know that male versus female comparison is discussing non-survival. So here, if it is positive or it is above 1, it means the older you are, the higher the odds or probabilities to non-survive. So if I'm discussing these two competing hypotheses about younger as those who have bigger chance to survive is correct one, according to these results. So that's the first insight, but still, the value is quite small one, and the scale for age is quite long one. So if you don't believe me, we can go into descriptives. Here it is, and we can describe age variable, and you can see that there are quite a lot of missing. That's out of this discussion, but still, minimum is some newborn child, 0.17 in years, and the oldest passenger currently here is 71-year-old. So this is quite long scale. And if you would like to interpret 1 year change for comparison of odds to survive or not survive, maybe this is not the best. So for regression models, once again, it doesn't matter whether we are discussing linear logistic regression or similar models. If your scale is quite long one, it is much better to use some other unit than only 1 unit change for the interpretation. So we can, for example, discuss difference between the oldest and the youngest member of Titanic. We can also discuss about the change, something like 10 years, 20 years, something like generation, etc., etc. So we would need some, I would say, real unit for this change interpretation. So some proposals, what would be our tool for the interpretation of age impact, and then I will show you how we can apply such computation. So 10 years, 20 years more. Some proposals, at least one proposal would be good.
Would it make sense to actually split people into, for example, 2 groups? The people
For the analysis, I would say no. It is much better if the variable is cardinal. Let's take it as cardinal. Currently, we need only some tool for interpretation, whether we will discuss about the change for also for non-survival by 10 years, 20 years change or something like this. So we need only this decision.
Maybe something like 15 years, because it is not as a big number for some older people to be dead, and it is influential for those who are 1 year old or even less.
Okay. So I will make a copy for this table. Here we are, and I would propose, for example, 20 years as generation change. Yeah, the youngest generation, middle generation, older generation, etc. could be found in my data maybe. And possibility how we can interpret such change. So there are 2 options. First option would be to take original coefficient, so it means 0.00635, multiply it by 20, and then exponentiate. So I would type function for exponentiation. And into brackets, I will type 20 times coefficient for age in Logit. Oh, there is some mistypo, I guess. I'm not sure what would be the problem. XP. Oh, yeah, I know. Here should be change symbols for decimal points. So it is 1.13 currently. So once again, it is currently comparing somebody who has some age and is 20 years older. And odds ratio for these two groups, once again, for non-survival, so it means that the situation is worse for those who are older, is 1.13. If you would like, for example, to compare the oldest one and the youngest one, so it means to take 70 years change, odds ratio for these two would be 1.5. But still, from substantive point of view, this is not very big difference. If you compare previous discussion, 10 or 12, male versus female, 1.5 for older and younger people, this is not very big difference. So according to my opinion, if I would like to compare the importance of these two predictors, so it means age and gender, so gender was very important, but age was not so important at all. That's my interpretation. And if you don't like to make this exponentiation of some multiplication of original units, you can also take other option. I would go here into odds ratio. It was 1.006. I once again need to change decimal separator. Here it is. And if I would like, once again, for example, to compute the change by 70 years, I would need to take the original value of odds ratio. And currently, if it is 70 years change, I would need to compute power by 70. So that's head symbol in Microsoft Excel environment and 70. And if I compute it, it should be nearly the same. So there are some rounding differences, but once again, 1.52. If I would like to compute 20 years difference, it would be 1.1112 as previously. So there are only some rounding problems. That's why these figures are not totally the same. So that's the trick which can be applied in logistic regression if you have long scale and you would like to interpret not change by 1 unit, but 10 units, 100 units, 1,000 units, etc., etc. So that's interpretation trick. Okay, so here we are, and we know about the impact of sex. Once again, if we control the age, and we know about the impact of age, and we know that this impact is quite big one in comparison with gender. And last one, variable that should be interpreted, that should be added into a model would be variable of class on Titanic. And once again, we know that there are 3 classes, and GMOV will do it for us automatically. That will create dummy variables. So once again, I would go into analysis, regression, binomial logistic regression, and once again, survived is dependent. Currently, age is covered, sex is the first factor, and P class would be the second factor. And you can see that automatically, first class is defined as the reference category. So it means it is outside of the computation. So if I go back into reference levels, so here I can see that the first category is the reference level. First category of the class is the reference level. For sex, it is female. That's why comparison male versus female. And you can see that also you can change here reference category for dependent variable. So that's quite flexible here. And if you change it, it will be directly recomputed. If you don't like to compute all results to the first class, of course you can change it, but I guess that for this first introduction, it is the best to take first class as the reference, as they have the lowest probability to die, and currently we are modeling whether they die or not. So that's why I would take it as it is. And for model coefficients, I would only ask for odds ratio. And currently, we can see also slightly different results from previous computation. So once again, the value for male-female comparison is slightly shifted up, and the final odds ratio is 14. So it means that also the structure of male and female in different classes were unequal. And currently, we have pure effect to be male versus female for dying on Titanic, which is nearly extreme, 14 times bigger odds ratio for male than for female. So that's it. The age, once again, we know that for interpretation, we would maybe make some increase such as 10, 20 units or something like this. And here we have two dummy variables, second versus first one and third versus first one. And once again, take into consideration that currently we are comparing people from different classes, but we are controlling their gender or sex and their age. So these two variables are under control. So once again, these are pure effects. And we can see that if you compare the second versus the first one, so for the second class, odds ratio to be dead was nearly 4 times higher. That's not a very small number. And if you compare the third class and the first class, it is 12 points higher. So if you take, for example, male from third class and compare it to female and first class, it is 14 multiplied by 12 times ratio. So it's for a huge difference if I take it as it is. Okay, my question, which is related to this result, is very easy, straightforward. Here I'm comparing second and first, third and first. What would be the ratio for third and the second? Can somebody help me and compute it? Without recomputation in GMovie.
1/4 divided by 3.6.
Yeah, definitely, you're right. So it's approximately slightly more than 3. Yeah. If you don't believe to my computation or my colleague computation, of course, you can change reference level. So for example, here I would change P class as the second one. It's very quickly recomputed, and 3.4 is second and third ratio. So here it is. So once again, I will go back to the first class. So here we are, and currently, I hope so, you have some basic information about logistic regression procedures, so you know how it works in GMovie and how to interpret basic results. And now, for a minute, and we do not have enough time, so maybe I will not open the second data file, and I will only go into some results here on Titanic data. So now, here for a minute, we will forget about properties of this Titanic data, and we will pretend that these data can be used for some generalization. So I will briefly discuss about generalization tools that are present in logistic regression. So first of all, once again, here we have some formal statistical tests, especially in this Z column and P columns, that are evaluating the impact of individual variables for us. Here it is that the age, for example, according to this result, is still statistically significant result. So it means if this was the sample for some people who were on some accident, so older people have higher odds not to survive. So it will be the result. The same for sex, the same for P class, and second one and the third one. We know that classical alternative to statistical testing is the evaluation of confidence interval of some coefficients. So if I go back into these settings, so you can see that in model coefficients, you can ask for confidence intervals for logits. they are not very useful at all for the interpretation, as also logits are not very useful for interpretation. So that's why I would ask for odds ratio confidence intervals. So here we are. We would get two new columns here on the right-hand side of coefficient table. And once again, if these data would be some sample, and I would like to generalize about odds ratios for age, sex, and individual classes, I would be reading these confidence intervals. So for example, our estimate for my data, so it means description for my data, male, female, gender ratio was 14. But if I would like to generalize to the whole population, once again, pretend that these are sample data, it can be as low as 9, but as big as 20.5 approximately. So this is estimate of confidence interval for individual coefficients. Second, first class, 3.7, 3.6, but 2.1 maybe 6. So here is also some, I would say, unreliability of our results based on the assumption that my data are sample and I'm generalizing to some bigger picture of population. So that's about the smart coefficient. Here we have confidence interval. So that's the next output. Now I will spend some more minutes about description of these model fit measures. And here, maybe the most useful, and I would go also into the presentation results, are so-called pseudo R-squares. So in logistic regression, we use nearly the same style as for linear regression. For linear regression, we apply overall f-test and so-called R-square, coefficient or index of determination, once again interpreted in percentages after multiplying by 100. In logistic regression, we have something similar, but it is called pseudo R-square. Why pseudo R-square? So once again, interpretation of R-square is that it is percentage of explained variance. The reason is that for linear regression, my dependent variable is cardinal, and I can measure variance somehow for this dependent variable. And my question is, currently I'm working with binary variable. Is there some variance computation for binary variable or not? Or can I apply classical formula for variance to binary variable, or it's useless? What's your opinion? No opinions at all? I guess that all of you passed at least some statistical courses. Yeah?
It's probably useless because like the variance should be.
Yeah, at least. Shouldn't be one. It is not constant still, but it should be some value. But it's not defined for binary variable. At least take into account that your binary variable can be coded as 0, 1, 0, 100, 1, 2, and it would influence also the variance, this style of coding. So that's not the best choice. So we would forget about the concept of variance currently, and it means also that these pseudo R-squares will not be interpreted as percentage of explained variance. So no multiplication by 100 and explained variance, but slightly maybe more difficult interpretation. So let's go to results. And here you can see, and don't ask me why this is default in Gemovi. There are big differences between individual packages, but here we have one of these pseudo R-square, which is called as McFadden. That's why there is index MCF here. So at least some properties for these pseudo R-squares. They must be in the range from 0 up to 1. There is no other alternative. So they are designed from 0 up to 1. So this is the same style as for classical R-squares. And as they are not based on some variance description, they are based on something what is called likelihood ratio value. So for every statistical model, also for linear regression, but for logistic regression, it is much more common. We can compute for every model something what is called likelihood value. And if you take likelihood for your model and compare it to likelihood of the model, which is including only intercept or only constant, then by different formulas, you can compute these pseudo R-squares. The rule is very simple. The higher is the pseudo R-square, the better the model is in explanation of your dependent variable. So I would like to see at least non-zero value. So here 0.32, according to my opinion, and according to my experience, is not the worst one value. So it means we explain at least something. We will discuss about some possibilities how we can evaluate logistic regression model next week also. So that's the first intro. And if you go into this model fit option, you can see, and once again, don't ask me why McFadden is default output. You can see also two other alternatives, Cox and Snell, and also Nagelkerke R-square. If I remember well the history of these pseudo R-squares, Cox and Snell was the first one, but unfortunately, it was proven that Cox and Snell pseudo R-square cannot reach the maximum, which is 1. And that's why Nagelkerke decided to somehow improve this property. And that's why we have Nagelkerke R-square, and McFadden derived also another formula. I would like to say that this Nagelkerke pseudo R-square is the most common in social sciences, so that's why I would prefer to use it. And there is also one more reason, which is not maybe the best one for application, but for all of these, so it means Nagelkerke, Cox and Snell, and McFadden, Nagelkerke is always the biggest one. So it is always quite good to see results that seems as better. So that's why maybe Nagelkerke R-square is applied. You can also find some more information in presentation, so I will skip into this. And there is also information that currently there is also very common to apply so-called pure R-square or pseudo R-square. I would say this is maybe the favorite, especially for statisticians, as properties for this pure R-square are maybe the best one, but it's not implemented in GMOV, it's not implemented in SPSS, it is implemented only in CHESP. So next week we will make a brief tour to CHESP and SPSS, so I will show you that you can also compute this. But once again, social scientists mostly apply Nagelkerke R-square, so they would type together to this analysis that explanatory power measured by Nagelkerke R-square for this model is approximately 0.48, and that will be all. There is mistake if you take this value multiplied by 100 and to say that explained variance for your model is nearly 1/2. That's not correct interpretation, as it is not based on variance. So that's about this model fit. And last one, what I would like to cover today is so-called likelihood ratio test. So if you go to model coefficients, to me the last option, which is not checked currently, so you would get a new one model, new one table, which would be evaluating by so-called likelihood ratio test statistical significance of individual predictors. So here we are, and we can see that individual predictors seems statistically significant if we use this old phrase, as all these likelihood ratio tests are attached with small p-values. So that's it. And you can also perform, it is in the previous option model fit, ask for overall test. So if you ask for overall model test, you would get the same test, but not for individual predictors, but for all predictors together. If you sum up chi-squares from this table and also degrees of freedom from this table, it should be the same. So if you sum up 28.5, 214.8, and 100.4, so you should get 330. Let's check it. And degrees of freedom 1, 1, and 2 is equal to 4. So here we have so-called overall likelihood ratio test. What does it mean? You are currently testing whether all these predictors together, if you take it into the model, are much better than if you would take only intercept or constant in the model. So in other words, it is the same as overall F-test in linear regression. It is testing whether at least some predictor is improving your model. And as p-value is quite low one, it means, okay, at least one of your predictors, so it means age, sex, and class should be included. And we know by this individual testing that all these should be included. That's added information here. So this is overall likelihood ratio test, and this is likelihood ratio test for every individual single predictor. So that's all what can be tested here. And I would only briefly visit here the dialog with assumption checks. And you can see that also here you can compute collinearity diagnostics. But I would like to say that for logistic regression, multicollinearity, it's not so big problem as for linear regression. And if you like to find more, for example, find some special points, or if you like to work with predicted values, you can go into save. You can compute predicted values, residuals, and Cook distance. And we know that Cook distance can help you to find influentials. So also influentials can be found here through this dialog. So that's all for, I would say, brief first introduction into logistic regression. So I guess that we covered nearly all possibilities of binomial logistic regression and GEMOVI. Next week, we will make complex example of, I would say, real data analysis based on sample. So it means all generalization will be correct. We will make also brief tour through JESP and SPSS to see how it works in competing platforms. And then we will skip into the topic of multinomial or polytomous logistic regression. So it means our dependent variable will have more options. But we know all basic steps for next week, I guess. I would like only to announce at the end that next week we will start at 9:30. So there will be a short lecture on again.